Hey, hello everybody. Welcome to this week's installment of our weekly reading group. Today, I'm very excited to be going through a very interesting paper from Anthropic, which is Towards Monosemanticity, Decomposing Large Models with Dictionary Learning. And what they do is they use a sparse autoencoder. They extract a large number of interpretable features from a very simple one-layer transformer. And they use this to think about how we can actually take steps towards interpretability of much larger models, which they then do on Claude Haiku in their follow-on work, which we'll cover in another session. But it's very hard to try to dive straight into applying these techniques to a very large model without having first gone through the basics and on a more toy problem. So for today, we'll just stick with their first one. So the link will be in the YouTube description, but for those on the call, I've just added the link that I'll be going through in the chat, so you can click here and follow along. And I'll be sharing my screen, and we can keep it quite open-ended and conversational to some extent. But I'll basically be going through this blog post, going through the key concepts and trying to explain it in a high-level way, basically. So let me get my screen sharing up. Here we go. So can everybody see my screen? Yep, it looks like it. I can see it. So, okay, I think we're ready to go. So I guess first a bit about the motivation. Obviously, large language models are generally these black box systems where text comes in, text comes out, and there's a load of neurons firing, and it's quite hard to make sense of why the model has made any decision, why it's chosen to phrase things in a certain way, why it's chosen to be kind or not kind or whatever. So it's generally very hard to understand why these large transformers make certain decisions. And it's also, as a result of that, very hard to control them, of course, because I mean, the only thing you can do at the moment is like try to explain what you want the model to do in the prompt. But as far as all of the intermediate internal representations and activations go, it has remained until recently quite I don't know, quite unclear exactly what's going on and what these internal representations actually are, and if they're interpretable at all. So the first thing they point out, which is very true, is that the neuron itself has turned out to not be a useful unit of human understanding. When you look at the tokens or the when you look at the tokens that one particular neuron fires for, very often there is no meaningful semantic interpretation to what's going on. It seems to fire on different topics, in different languages, on different points in the sentence, and it's very hard to extract semantic meaning at the level of neurons. They say that one potential reason of this is that there is polysemanticity. Well, one reason for the polysemanticity, and polysemanticity, so semantic means, just kind of meaning. So semantic means something that has kind of an interpretable fixed meaning, poly meaning many. So polysemanticity, meaning that a neuron seems to have many different things that activate it, many different semantic reasons that it's activated. And one argument for this is superposition, where a neural network represents many more independent features than it has neurons. So a network that has 512 neurons might be representing, thousands or even tens of thousands of independent features. In the same, I guess one analogy here is kind of in the same way that, 8 binary digits can represent 2 to the power of 8 different numbers. There's some kind of like analogy here. Obviously, these features don't quite just turn on and off. The features have magnitudes as well. So it needs to do a little bit more than binary numbers do when you have a small number of digits that represent a large number of features. And also the neurons need to be able to have the ability to to have multiple of these features turned on, not just one of them. But the general idea is that there is a small number of neurons, but there's many, many more features which combine together to then turn these activations on at the neurons. But we'll go into that in a bit more detail. But one of the key concepts of the paper is that this superposition is what's going on. And actually the true features that are actually being used by the network are these kind of latent features that we need to detect and kind of learn. And they're not immediately present in the activations or in the neurons, basically. So they use a weak dictionary learning algorithm with a sparse autoencoder. We'll go into the details soon, but they basically are able to take the activations, train a sparse autoencoder on those activations, and then they do this on a reconstruction loss, which is what autoencoders always do. They take the input, they need to reconstruct the output with some kind of regularization losses applied as well. And the intermediate representation of this sparse autoencoder are these learned features, which are then much more interpretable than the neurons themselves. So this is the high level motivation. So the first thing they do is actually just show us a lot of the features of what they call their A1 run, which is basically a run where they extracted 4,096 features. So basically the number of semantic features that are extracted is human controlled. It's basically what is the hidden state size in the sparse autoencoder, and you can control how large or small this is. There's 512 neurons. So this is an expansion of kind of 8, and they use this A1 run with 4,000 features quite a lot because they seem to think this is a good balance between having specific features that aren't too broad, but not like super granular features, which start to emerge when you have a bigger hidden state in the autoencoder. So this A1 run with this many features is a staple throughout the paper. And the first thing they do is show all of these. So one thing you can do if you follow the link I shared is you can literally go through what are these features. They identify 49 clusters, and each of these features has a particular semantic region, has a semantic meaning. So for example, this feature is for markdown citations, and it predicts the year, basically. This one is the token ref. Well, actually, I'm trying to. So ref in context, I think this is related to, for example, academic citations. I think that's what I was referring to. This feature refers to the like subword sec. This feature attends to references to figures and tables. So that they end up having these features that do a mix of quite general, quite specific things, but all of them are human interpretable, and all of them, when you look at the things that activate it, have a consistent meaning, much more so than the neurons, which are totally. So this feature attends to bibliographic citations or references, firing most strongly for formatted citations with brackets. So again, like very clear, specific situations in which these features attend, and there's many of them. So obviously, we were just looking at one particular section here. They're not all about academic papers. We were just on one cluster there. You can kind of go across here and see what the semantic meaning is for a lot of these. So this feature fires when it sees words about physical interaction such as hands, arms, fingers, etc. So again, they've got these 4,000 features which are semantically interpretable, which is not the case with neurons. So they kind of start with like the main findings, which I think is not a bad way of starting, just so we kind of know what's in store and what the main findings are. So to kind of go through their main findings, so they do find that sparse autoencoders do extract relatively monosemantic features. So monosemantic, again, meaning that each feature is responsible for a very specific thing, and it only fires when that specific thing happens, unlike neurons. They provide 4 different lines of evidence. So they show investigations for a few features firing in specific contexts where they can construct computational proxies. So yeah, they find a way of like computationally computing when the context is true, and then verifying that this feature does indeed only fire in those contexts. They do this human analysis where they get humans to kind of assess the interpretability. They do an automated one that uses AI to assess the interpretability of the activations. And then they do an automated analysis of the logic weights. So, but again, I think we can go into more detail when we get to that section. But aside from just looking at the features and assessing how interpretable the bits of text that it fires on are and how consistent they are, they also look at artificially activating that feature and seeing how that affects the probabilities of the tokens in the text. And they see that when you activate the Hebrew language feature, the LLM then is much more likely to output Hebrew, and it does. So you can kind of turn these features on and off, and you can then directly impact the output of the final system, basically. I don't know why updating the event didn't solve the invite problem, but hey ho. Yeah, so they say that they're basically invisible in the neuron basis. So when you actually look at the neurons, you cannot see any hint of these semantic features directly in the neuron. So it's very rare that one of these features are mapped directly to a neuron. So you need to kind of, you need to learn these, you need to detect these features through learning. And they can be used to intervene and steer transformer generation. So you can, when you have these semantic features, turning them on and off directly changes the LLM. So you can kind of turn up the feature that's like praise and it will give more praise. You can turn up the feature that says, I don't know, be very strict and it'll be more strict. And you can kind of directly tune all these knobs to steer the LLM output, which is very interesting. Much more granular than anything that can be done with, just RLHF or anything like this. They also see that sparse autoencoders produce relatively universal features. So they do this test where they take different random seeds and they train the same architecture on the same data with a totally different initialization. And they see that the same semantic features are learned, which is very different to neurons. Obviously, the neurons end up being totally different, but the semantic features have very strong consistency, which suggests that there is some universality to the features that these networks learn, basically, which is also very interesting. They only do this across the same architecture and the same data set. I think they leave it to future work to look at how much this transcends architectures and data sets, but they already show some indications that it's true because they refer previous works and the semantic features that they've uncovered, and they find many of the same semantic features being learned in this case, which is a different architecture and a different data set. I mean, this is a one-layer transformer, so of course it's different to some of the other prior works that have applied this to much bigger models. And then the other very interesting thing they see, which they said is surprising, is that as you increase the number of features that you're detecting, so as you increase the latent size of the autoencoder, and you're kind of extracting more and more granular features, you see features effectively split. So if you were trying to find 512 semantic features, you would maybe have one feature that corresponds to, I don't know, physics, let's say. I'm making this up, but like physics, let's say. And then when you go to 2000s, maybe that physics feature splits off into quantum physics and particle physics and astrophysics, and maybe at 4000 it goes to kind of, I don't know, it goes to kind of like, neutrino physics or kind of atomic physics and chemistry, and it goes to kind of general relativity or whatever. So you have this kind of natural case where features, as you get more and more, do split off into more and more specific, but consistently monosemantic features as you increase the size, basically, which is very interesting. And they make this point that just 512 neurons, which is a very small number, can represent tens of thousands of very clear features. So despite the MLP layer being very small, they continue to find new, very specific, granular, interpretable features that only activate on a very specific context as they continue scaling up. And they believe that there is a true number of features where when you get past this number, there are no more features that are determined. But it's actually, potentially tens of thousands, even just for 512 neurons, which means that, big LLMs might be learning, billions of features potentially. Well, way more than there are activations, basically. Yeah, and then what they see is some very simple examples of how these features, by simply effectively turning on and off, you can end up with these kind of finite state or automata where these systems can, one feature turns on, that means it knows that in the next iteration, that's going to make other features more likely to turn on. And you can end up having these kind of like almost like logic gates where you turn one thing on, turn one thing off, and you know how that's going to impact the turning on and off of features on the next step. And you can kind of propagate information forwards, taking this purely feature on and off perspective, basically. I also think this is very interesting in the context of things like 1-bit and 1.5-bit LLMs, because if we effectively have this like much larger set of latent features, which are effectively just turned on and off, it does make you wonder like how this then might project into effectively more binary style activations, even though it's the weights that are binary and the activations aren't binary, of course. But anyway, so that's just something that I think is very interesting, because obviously these 1-bit LLMs continue to learn, pretty much almost just as well. So presumably these latent, very semantic, understandable features are also being learned in the 1-bit case. And I think there's some, interesting kind of work to be done there. Okay, so that's kind of the high level. I mean, I guess, so this is an incredibly long paper. I'm going to try to my best to like not get bogged down into it too much and to keep it as high level as possible. I haven't made slides, so I'll go through, you know, some of the key findings rather than going into all of the crazy detail, and try to keep it settled like that. I guess firstly, just the general kind of problem setup. Does the general motivation for this make sense on a high level before I keep going? Any kind of open questions before? They can be very silly, naive questions, or is everybody happy broadly with the kind of motivation for this work and some of the high level stuff? Okay, well, I'll dive in then. So in terms of the problem setup, basically what they are doing is they want to basically take these activations. So this is their model. It's an incredibly simple one layer transformer where they have the tokens, they compute the embedding, they then have these states, they do the self-attention, then they have an MLP, and then they add this to the output from here, and then they embed and get the logics, basically. So this is the entire neural network architecture. This whole thing with these light gray boxes is their transformer. So incredibly small, and they have these 512 activations after the MLP. And what they want to do is to try to decompose these MLP activations. So that's important. It's not the weights, it's the activations. They want to try to decompose those with a sparse, overcomplete autoencoder, so that they can get a number of features which range from 512 up to, in their experiments, 130,000. So the question is, can we decompose this set of 512, these 512 activations into this much larger number of features which combine in a linear manner to create these activations? And are these higher kind of dimensional features, are these interpretable in a way that the activations themselves from these neurons are not? This is kind of the framing of the question. So the way they do this, so they decompose it into more features than there are neurons. This is because they believe that the MLP layer likely uses superposition to represent more features than it has neurons, and correspondingly to do more useful nonlinear work, of course, because the more features you can extract, the higher performing, of course. In fact, in the large experiments, they expand to have 256 times more features than neurons, and they see that new features continue to emerge, which are semantically consistent and very specific, suggesting that there are, in fact, many, many features that are kind of being uncovered behind the scenes, basically. So what they do is they have this. So again, the transformer, very simple: one attention block, one MLP block. The MLP size is 512. So tiny, tiny transformer. They do all of the experiments on a data set which contains 1 billion tokens, and it's trained in the standard autoregressive log likelihood manner. Now, the sparse autoencoder, also very small, has one ReLU on the up pass, one linear on the down pass, and the MLP size varies from 512 when we're trying to detect the same number of features as there are activations, up to 131,072, which is a massive expansion. And the data set is basically the activations of this model on this data set, and they take 8 billion samples. So they take a data set of 8 billion activations of these 512 activations, and all they do is they have an L2 reconstruction, which is what an autoencoder does. For those that don't know, the whole point of an autoencoder is to take some input and to map it to the same representation. So you basically try to duplicate the input, but you pass it through some intermediate representation to try to extract some latent code representation of the thing. So typically, actually, autoencoders do the opposite. Like the most common use case of autoencoders is to go from a high dimensional space to a low dimensional space and then back up to a high dimensional space to try to get a compressed representation of the thing you're trying to learn. But in this case, obviously, it's the inverse. We're going from low dimensional to high dimensional back to low dimensional to try to see if there are a larger number of features that represent the low dimensional. The way they constrain this is by having an L1 loss on the hidden layer, as we'll see in a moment, because they want to make sure that the feature representation is sparse. So they want to see if there is a setup where there is a very, very large number of features, but only a small number of these features are ever turned on and combined to create the activations. So almost like a dictionary, like there's a huge number of features, most of which are turned off all the time, but occasionally you turn one or two of these on, you combine them, and that's how you get the neuron activation. This is kind of hypothesis, and this L1 regularization on the hidden layer forces the representation to be as sparse as possible. So we have a small number of activations at any given point in time. So this is how they extract the features. Relatively simple, and they motivate this more in more length. I think maybe I'll skip past this because it's kind of explaining what I just described there. So they give some more explanation for features of decomposition. Basically, their idea is that X superscript J is the activation vector for a data point J. So this is for so it's the activation vector. So this is a vector of 5 to 512 for a particular data point. F sub I of X super J is the activation of feature. So there are the index here I is across all of the features, and the idea is basically you look at how this feature is activated on this particular for this particular token, basically, because J is like the data point, let's say, X is the full vector. You basically go across and you sum up every single monosemantic feature that we've uncovered. You multiply this by its unit vector is this direction, which comes from the columns of the matrix in the autoencoder. You sum all of these up and you have some bias terms. So basically the idea is that the activations come from a linear combination of the learned features, is the way to say this. So it's a fully linear mapping. You have these monosemantic features which apparently sum up to create these vectors. So you sum up all of these monosemantic features which each have their own particular direction in this space. You sum all of these up, and then what you end up getting is the final activation vector from this, basically. So it's a fully linear relationship. Yeah, and then the way they do this is that the way they extract the feature activations is basically from the weights in the autoencoder. So they have the activations. They then have the weights of the encoder. They then have a bias, a pre-bias and a post-bias term. They pass it through a relu, and then they get the feature activations, basically. So it's all a linear relationship. The pre-encoded, the encoder bias. And then the feature directions, so these D sub I, the feature directions are the columns of the decoder weight matrix, W sub D. And again, they have an appendix where they go into lots of detail. But I mean, suffice it to say, if you're not following along the whole details, they have this very shallow linear autoencoder, and you're trying to basically learn these features which linearly combine to create your activations. And the features are meant to be monosemantic and interpretable. The activations are provably not interpretable because these are the neuron activations, and this is kind of how we structure it. And the way that we encourage this to be sparse, so that only a small number of these features turn on when you're doing this large sum over all of them. Most of them are off, some of them are on. The way that we enforce this is by having an L1 loss on this intermediate representation of features, basically, when we do the learning. This is kind of the high level of what's going on. Okay, any questions so far from any of this? Nope. Okay. Okay, I'll assume it's making sense on a high level. So the hypothesis really here is that there is this the superposition where basically you have this like hypothetical disentangled model where every single neuron activation is monosemantic, is totally individually interpretable. But actually what we end up learning is this observed model where basically these idealized neurons, which are all independent and have their own clear unique semantics, are effectively projected onto the actual network as an almost orthogonal vectors over the neurons. So so effectively what they say is that when you train a model, you're effectively learning a simulation of a much larger network where every neuron is a totally disentangled feature. That's one way of looking at it. And you can say this because obviously, like, you can make all kinds of arguments as to why this might be happening. But of course, a model that's able to represent more features is higher performing. And so if you're really trying to descend the loss function to get the best performance, you're going to want to push the capacity of the network to its absolute limits. And you're naturally going to be leveraging superposition to represent as many features as you can, which gives you the more expressive model. And you're going to then end up basically having like a simulation to some extent of a much larger model that has many more features representable, basically. That's kind of one way of thinking about this. So basically, a good decomposition. I'll skip through this. Oh, my headphones are dying, actually. Hang on. Let me very quickly, I'll pause this on the live one, but my headphones have just died. Let me very quickly change these over. Sorry, one moment. Okay, that should work. People hear me? I think so. I'll assume people can hear me. Okay, I can see my thing moving, so they can. That's good. Okay, awesome. Cool. Also, sorry, just to test in case I miss anyone. Ved, can you just quickly like say hello or something? Just make sure my headphones are working.
Hello.
Yes,
can you hear me?
Yes, I can. Perfect. Thank you. Cool. Okay. So, so they say why not use architecture approaches? I've skipped through this. I mean, it's very, very dense, but basically there's other ways you can do this. One thing they've done in their previous work is that instead of training a normal network and then learning an autoencoder, what they did is they actually added some inductive bias into the network itself to try to encourage the activations to be monosemantic. So the network trained on the entire data would be forced to have these understandable features. And that kind of worked, but it just had much worse performance. And they ended up coming to the conclusion that this isn't really feasible on these very large models. And therefore, it's much better to learn the network as you normally do, and then to try to detect the features using some autoencoder after it's been trained, basically. So this is kind of the motivation they give. Using sparse autoencoders, there's a lot of ways you can do this. They make the point that it's an NP hard problem to try to find the perfect set of high-dimensional sparse features that can represent the activations. They make the point that, like, even though there might be better ways of learning this than having a very shallow sparse autoencoder, their point is that whatever sparse features, whatever sparse monosemantic features the network is reasoning with cannot be so hard to uncover, because if the network's actually making use of them, it makes more sense that it's like, you know, a linear projection and a simple, it can be simply recovered from such a shallow sparse autoencoder. So they don't want to make the relationship too complicated, and therefore, if it can be learned with a very shallow sparse autoencoder, it's more reasonable that the network is actually able to kind of reason about these high dimensional features, basically. Yeah, that's kind of, yeah, they say it's here and be hard. So despite its difficulty, yeah. They have a concern that iterative dictionary learning might be too strong in the sense of being able to recover features from the activations which the model cannot access. So given that it's NP hard, the neural network certainly isn't doing anything that's NP hard. So a sparse autoencoder is very similar to the MLP. So the network should be able to reason about these high-dimensional features, basically. I talk about the setup, but I think we've already covered most of this. It's an L1 loss to encourage sparsity. It's 8 billion training examples. They noticed a few things that they found so there's a few little details that they, over the course of training, some neurons cease to activate even across a large number of data points. So resampling these dead neurons during training give better results. There's lots of like finer details, but for the purpose of an hour-long, thing, we don't need to go into all of that. Then they talk about how can they tell if the autoencoder is actually working, and this is actually what the most of the rest of the paper covers, which I'll go through. Basically, they do a whole load of different experiments to verify that the features they learn are indeed more monosemantic, are indeed more interpretable, and we'll go through those. Rather than explaining what they do, let's actually go through it and see what they do. The one-layer model they're studying, the reason they do that is because they want to keep it self-contained. It's already incredibly computation expensive to train this on 100 billion tokens or whatever, and then train the autoencoder on 8 billion tokens, and to do all of this like very exhaustive experimentation makes sense to start with toy problems first, and nobody's done this for a one-layer transformer, so that's their starting point. They have this notation for features, which is A /number/number. A represents the model. So if it's A, it was the first set of random seeds for the weights of the transformer. If it's B, it was the second set of weights, the second random seed. 1 then represents the run they did. So whether it was 512 or 1024 or 2048, etc. And 1 represents this one that they use for most of the paper, which was with 4096. But they have other runs as well. You can see all of the runs and all of the detail in their interactive plots, which is really, really awesome. So literally every single granular piece of information you might want to look at, they've got it all there in these interactive dashboards that you can look at, which is through this interface. So I'd recommend you go check this out if you want to learn more and really see what's going on. But for now, I'll skip over exactly how this interface works. And they have another interface as well. But let's go into the detailed investigations, because I think this is where there's some interesting stuff. So the most important claim of the paper is that dictionary learning can extract features that are significantly more monosemantic, again, meaning singular meaning, than neurons. And in this section, they give a detailed demonstration of this claim for a small number of features which activate in very specific context. And the reason they do this is because these features can be programmatically tested for activation, so they can kind of have a ground truth for these features, unlike they could for more abstract features like, you know, the concept of love or something. So that the 4 they test on is text written in Arabic script, DNA sequences, base 64 strings like the final characters of the YouTube URL, and text written in Hebrew script like so on. And for all of these, it's very easy to write a script that can take all of the corpus of text and, like, using some relatively simple programmatic logic, determine if the text indeed is one of these 4 things, because, you know, you never see sequences like this unless it's DNA. Hebrew is very specific. Arabic's very specific, Hebrew is very specific, etc. Yeah, and the questions I want to answer are these 5. So are the learned feature, does the learned feature activates with high specificity for the hypothesized context? So it only activates in this context and nothing else. Does it activate with high sensitivity for the context? So when the context is present, it's usually on. So this is kind of like false positive, false negative kind of thing. So, like, you know, does it only activate here? Does it always activate here? The learned feature causes appropriate downstream behavior. So when you turn the feature on, does it impact the output of the network? Is it the case that there's very clearly not a neuron that this corresponds to? So, you know, the closest resembling neuron doesn't represent this semantic feature. And is the learned feature universal? So if we then train another model with another seed, do we get the same feature emerging again? And basically the answer to all of these questions, to, like, cut a long story short, is, you know, yes, it is universal, doesn't correspond to a neuron, does cause downstream behavior, does activate with high sensitivity, and it does activate with high specificity. And that is the case for all 4 of these. So really, really very strong, compelling evidence that there are these monosemantic features that the network is learning. So again, they talk about the fact that when you have a limited number of features, so what they would imagine in a polysemantic typical, so you expect that you have all of this data, and then you have these feature activations, and where features are more specific than proxy. Yeah, okay, so basically, like, in a polysemantic setting, you would have a feature that fires in many unrelated contexts. So if this circle represents the context, like a neuron, you would see firing on all of these different data points that are totally unrelated. Now, if a feature only activates when there's a particular proxy, then you can rule this out, and it will only fire in some semantic space. Like, again, the circle representing, like, you know, all different semantic concepts, let's say. But what they find is that particularly what they find is that when features end up being more specific than the proxy, so when you have a lot of these features, so you have many of these features learned with a very large autoencoder size, what you end up getting is that multiple of these very specific features fire together to represent high-level concepts. So you might have, like, you know, a physics passage, and one feature is like, I don't know, a woman is talking, so you say she and her. Another feature is it's about particle physics. Another feature is, well, actually no. So in this case, it's about in one proxy. So it might be the case that one is about particle physics. One is that it's in a lecture about physics, and one is that, I don't know, we're talking about like post-relativity physics, I don't know. But like the idea being that when you get these very specific features, you can end up getting them fired together to create a high-level proxy from their kind of composition, basically. Okay, so diving into the graphs and what these mean. So I'll explain them all for the Arabic case, and then we can go through and look at it for the other ones. Basically, what they have here is they have the feature activation level on the x-axis. So we go from low activation to high activation, basically. They have this programmatic way of determining whether or not a given token from some text is likely to actually truly be Arabic or not. And they do this by basically doing this. The estimated log likelihood ratio is as simple as this. It's the probability of seeing this symbol in general text over the probability of seeing this symbol when we know that it's Arabic script. So it's super simple. It's like, you know, what's the increased probability of seeing this in this context, basically. So a very simple way of assessing how likely it is that we're dealing with Arabic script. And when this log likelihood ratio is high, it's red. When it's low, it's blue. And what we then see is basically when this feature activates, for low activation levels, there are, and this is the density. So this is how many tokens were activated, how many tokens there were at each of these different feature activation levels of this Arabic feature, basically. And we see at low feature activation, there's quite a lot of non-Arabic that's activating. For example, the sum here where it activates on the word copyright, it activates on a few things here where it's not actually Arabic text, but some of the tokens are being used because of some, I don't know, kind of encoding or something, basically. But then what you see is that as the feature activation becomes higher, the proportion of the text, which is indeed Arabic, gets bigger, basically. So the fact that as it gets larger, we see more and more red suggests that this feature is indeed very selectively firing on Arabic text and nothing else, basically. And this bottom graph is just this same graph here, but normalized to a bar, basically, just so you can see the relative red and blue split without being distorted by the density, basically. Yeah, any questions on what this graph is representing at all? I realize it's quite complicated, so it might be one that people need to rewatch a bit. But this is basically proving that this feature uniquely activates when there's Arabic text, and particularly when the activation is high. When this feature has a long the model may still be imperfect. That's why we might still see some of this. This was on the 4096 run, but they say if the true number of features are 10,000, then of course you're going to have some noise because you're going to have a large number of features being projected into a smaller number of features. So you're going to have like some maybe other features kind of creeping into this feature. So it's not totally monosemantic. So that's one reason why we might see these blue regions in the low feature activation level. The autoencoder may be imperfect. The L2 loss never gets to 0. So the autoencoder never perfectly represents the input of the activations, which means that it means that the linear combination of these semantic features are not actually perfectly representing the activations because the L2 loss doesn't go to 0. So there's all kinds of reasons why these features may be imperfect. But yeah, this is some of the explanations they give. What they then say, though, is that obviously in terms of the causal effect, high activation levels have a much bigger impact on the network performance. And therefore, a very common representation is to actually weight these by the activation level. So if you imagine coming here, but you multiply each peak by its activation level. So this, this is 4, it's like, let's say like 4.5K. We then times this by 7, we times this 3K by 6, and then we look at the graph. This is what we get, which is more indicative of the importance of each of these activation levels on the network performance. Because of course, when you have a feature activation of 1 or 0 or 0.1, it has a tiny impact on the performance of the network. So it doesn't matter that much that this Arabic feature is firing on these non-Arabic tokens, because it will hardly have any impact anyway, basically. So this is what this graph kind of shows. Okay, then they do another analysis, which is if we turn this feature on, if we artificially kind of turn this feature on, how does this impact the probability of tokens in the output? Does it make Arabic text more likely to be output than it was before? And what they see is, first of all, there's this big peak around 0 where many tokens become, most tokens have no impact. So the vast majority of tokens are not changed at all. But there are some tokens which are changed a tiny, tiny bit. So you have this kind of interference, basically, where changing something, of course, makes all the tokens a bit more or less likely, but generally by very low magnitude. So the weight, the amount by which this token becomes more or less likely is small magnitude, but there's many, many of them. So most tokens have a small change, let's say. And then on the far right-hand side, where you have a big change, a big positive change, you end up seeing these second moments where it's on Arabic text. So, the tokens that have a big increase in likelihood are the Arabic tokens. So again, it shows that this actually causally impacts the output of the LLM, basically. That's what these graphs are showing. And again, this is the same. This one here is just normalized across the height. So obviously you can't really see it when it's kind of got this density, but you can normalize it here and see that at the 0.4 to 0.5 range, all of the tokens that are made likely are Arabic tokens. Any further questions on this plot at all? Okay, so we've shown that turning these features on causally impacts the likelihood of the output of the model. And they do the same here, where they see like which tokens were made more likely, which were made less likely, and they see that all of the Arabic tokens were made more likely, and the dot was made less likely in this random sample of text, basically. They also see that if they turn it on, what happens is that, because it's a tiny model, bear in mind that a good LLM would be able to go 11, 12, 13, 14. This is a one-layer model, but what it does is it goes, starts giving random English numbers after this prefix. But if you turn this activation on, it suddenly starts outputting Arabic. So again, just proof that it does causally change things. So another question is this feature just a neuron? Like, it's all well and good that we've detected this Arabic feature, but is this not just basically one neuron doing all the work? And they make the point that no, when they look at the activation basis, so when you kind of like get the activation vectors and how they linearly combine to create the feature, and they look at which neurons are relevant when using an activation basis, they basically see this. So across their 512 neurons, you have some that are very positive, some that are very negative. There's no clear individual neuron that accounts for this feature more than others, basically. So the feature is very monosemantic. Yeah, and then they look at the coefficients of the features using this neuron basis of the feature, and they find that the three largest coefficients by magnitude are actually all negative. So the biggest impact is that these neurons having them low values makes this feature more likely. And there's 27 that are at least 0.1 in magnitude. So basically there's not one single neuron. What they then do, they say it's of course possible that these neurons engage in a delicate balance of cancellation, which is true. So there could still be one neuron that really turns this on and off, despite all of these coefficients. So to check for this, they find the neuron whose activations are the most correlated to the features activations over a very large data set example. And the most correlated neuron, which is this A489, responds to a mixture of non-English languages. And they can see this by visualizing the same activation distribution for the neuron using this log likelihood ratio for Arabic text. And again, looks nothing like it. The vast majority through all levels of activation are not Arabic. They're just general text across all languages. So there is no Arabic neuron, but there is an Arabic feature in this high dimensional space. Okay, and again, same with this. So when they turn this neuron on, it doesn't make Arabic more likely. There's no clear second mode at all again, so emphasizing the point. And then what they do is they look at the correlation between the neuron and the feature. There's actually a mistake here. I think this axis should say feature activations run a neuron. This is not run B because the universality thing is here. So this is a typo. Basically what we're seeing here is the correlation between the neuron on the x-axis and the feature on the y-axis, and there is very little correlation. There's a 0.21 correlation. And again, the colors here represent this log likelihood ratio. So when it's red, it means that it's Arabic. When it's blue, it means it's not Arabic. And the feature and neuron don't correlate, basically. Most of the stuff here is just kind of inference weights, basically. Okay, and again, obviously, the fact that so much of this is red on the activation and so little of it is red on the neuron, again, emphasizing that the feature is activating on Hebrew and the neuron is not. Okay, any questions on these graphs at all? No, okay. So then, interestingly, they have this universality debate where they say, okay, well, that's all well and good. We trained our model A, and we detected this Arabic feature, but is this a universal feature? Like, if we trained it again with another random seed, would we get this exact same semantic feature appear again? And basically the answer is yes. It seems like this feature, regardless of totally different initialization and totally different neuron weights, which look totally different across the two networks, there is strong consistency in the semantic features that are learned. So it would just indicate we are discovering something much more general about how these learn to represent different representations on the data set, which is very repeatable. So they search for a similar feature in B1 using dictionary learning again, and they find that the closest activation has a correlation of 0.91, which is very, very similar. Not exactly the same. In fact, they see this one's even better. This one has a better performance on the activation level in the low regions before we had quite a high one here. And then again, very, very high performing in the 5 to 6 ratio. So it seems like we've learned a very similar feature. Again, it has this second mode. When you artificially turn this feature on, it makes Arabic letters more likely in the output in a very similar way to the previous one. And when we look at the correlation between these two, so now we have features on the X and Y axis, so there's no neurons here. We're looking at the correlation between the Arabic feature in run A and the Arabic feature in run B, and we see a very high correlation in the feature activations of 0.91. We see a low correlation in the logic weights, but this is, as is discussed later, this is mainly because of this interference, where the vast majority of the impact of turning this feature on makes a small update in the probability for most tokens. Most tokens are either made a bit more likely or a bit less likely, but the only ones that are made significantly more likely are all Arabic tokens. And they actually come up with some better plots to represent this later on, which has a much stronger correlation coefficient. But they also hypothesize that because all of these other tokens are so low probability anyway, it doesn't really have a negative impact on the output to slightly increase or decrease their probabilities, because you're slightly increasing or decreasing the probability of the 500th token selection. That doesn't change the output, basically. So that's kind of why this actually doesn't matter too much. Yeah, okay. So what I'll do, because I don't want to go on for too long, what I'll do is basically say that the story repeats. So they go into a lot of detail about a DNA feature, exactly the same thing as seen. Although no, it's not, because their log likelihood ratio was quite broken. They realized that the way they do this fires quite negatively. But what they do still see, looking at this graph, is that on high activation levels, it's very high probability DNA. On the low activation levels, it's not, but that's mainly because of an issue with their log likelihood ratio, where they get a lot of false positives, as they demonstrate here. There's lots of cases where the proxy misfires very, very often. So they think most of this blue region is a broken proxy. But otherwise, it's very similar. Kind of, again, we have this big interference weights followed by very sharp, specifically DNA tokens that are made much more likely. They see something similar with the activation. So the neuron, there's no neuron that corresponds to DNA. Same with universality, very low correlation. Oh no, this is universality, sorry. So high correlation with the two features. Same again, base 64 feature, same again. There's some slight nuances here. The mode of this one is not quite as pronounced, and they say that's because obviously base 64 text is a lot like any text or English text very often, so it's not quite as well separated in terms of the likelihood, but there is still a quite clear second mode, which is stuff that's very clearly base 64 text. They get the Yeah, similar results in terms of universality as well. So basically, the run A and run B have very strong correlation. The feature is not a neuron, again, emphasizing that there's no similar neuron. So they get the same kind of results on all of them. The same for Hebrew as well. It's basically the exact same logic applied repeatedly and repeatedly showing this feature has monosemanticity. There is no equivalent neuron. It does increase the likelihood of text in the output. It is very specific, and so on. So they've proved this same point 4 times using these 4 features where they could programmatically detect it in the text so that they could actually have a ground truth. They then do some really interesting global analysis where they basically look at features and they say, here is all of the different contexts in which this feature fires. How interpretable does this thing seem? And it's done in a blind manner, so you don't know whether you're looking at a neuron or a feature, kind of a blind, randomly ordered manner where there's like all these activations and all these activations. Which of these two, how interpretable does this thing seem? Like, do you think there's a pattern here that can be detected? And this was using like human experts, and they see the features score much more highly than the neurons. So the features as per experts are much more interpretable, and you can come up with a story as to why this is activating much more than you can with neurons. They did the same with AI. They asked AI to predict the interpretability, and then they went one step further and they asked the AI to predict when this feature would activate on unseen text, and then they use the accuracy as a proxy for interpretability. So you basically get like all of the contexts in which this feature or neuron turns on. You ask the AI to explain what the context is, and then you ask the AI on an unseen piece of text to predict which tokens will be turned on with this feature. And it's able to do that much more predictably with the features than it's the neurons. So again, like verifying again that there is objective meaning to these features much more than there is with the neurons. They did the same with the logic weights. I forgot what they did here exactly, but yeah, like predicting what the next output token would be, something like this. They talk about a few caveats. I want to make sure there's a little bit of time for questions and not run over too much. They show these examples where obviously when you turn on these semantic features, you can then suddenly get 1, 2, 3, 4, 5, 7, 8, 9, 10, no intervention, it starts giving more numbers. You add the Han Chinese feature and it starts replying in Han Chinese. You add the DNA feature, it starts replying in DNA. You add the uppercase, it starts saying so in uppercase. So these features can basically be turned on and off and can directly impact the output from the model, basically. They talk a bit like philosophically here about what this means for generally understanding the model. Are these the real features? Is this actually kind of the ground truth of what's going on? Is this just a representation? Is this potentially a projection of the data more so than a projection of the model, given that these are activations? So these are very much conditional on the data fed into the model. The activations obviously come both from the model weights and the data fed to it, but the fact that turning these features on directly impacts the output of the model suggests it's something more fundamental about the model itself. And also what they do as well is they ran an experiment where they took an untrained model and try to do the exact same thing on the activations of the totally random weights of the transformer, and there was no semantic features there. So these features are certainly not only a property of the data being fed through a random matrix multiplication, it is very much a feature of the network, because you need a trained network for any of these features to be detectable at all. They mentioned that you have this very clear feature splitting. They imagined that there would be this kind of isotropic distribution of features, like relatively uniformly spaced in the latent semantic space. What they actually find is that when you go from 512 features to 4,096 to 16,000, you end up getting these clusters that then split. So you get these features on run A0, and then when you multiply by 8, you end up getting the same structure, but with a smaller number of features becoming more specialized in each of these kind of semantic regions. And that's what the dark green represents. And then the light green, the smallest, represents even more granular fracturing, where the features become even more monosemantic, even more specific, and can then start to work together to create these kind of high level concepts. When, like 3 or 4 of these turn on, and then you have this kind of compositional concept emerge, basically. And that's very interesting. It's actually not what the authors expected to see. So yeah, I'll skip through this. You can go through the finer details yourself. They make one point that not always it's splitting. It's not always a tree. Occasionally, you get several features merge into one as you go more granular. But generally speaking, you get concepts that split out, broadly speaking, or the context changes a bit. You might get one feature then kind of splits into two that then themselves split off and stuff. So it's not just a tree. It's a little bit more complex, the way that the feature splitting happens. And yeah, I'd recommend going through all of this. I'll try to keep this to broadly an hour. But I think the high level concepts have hopefully come through. One of the final points they make in all of this is that, yeah, this interesting observation that I'd suggest you read through is just that, like, another kind of representation of how LLMs work is that you effectively, it seems as though there might be this very finite number of very clearly defined features that represent very specific things that effectively turn on and off. Like the low activation region is more noisy, and effectively you have these very sparse number of features. You can imagine tens of thousands. In a large model, it would be hundreds of thousands of features that represent very specific things, like a dictionary. These then turn on and off on any given token. And the fact that these are turned on and off directly impacts which ones will or won't be turned on and off on the next section. So you can imagine this kind of like, array of buttons, and you press some of the buttons and that gives you something. And then on the next section, like a logic gate, that says, okay, well, these buttons need to turn on next time. And you can end up getting this kind of very state machine-like representation of how transformers propagate information across each token and how they store information for the next section. And it's very much by turning these monosemantic features on and off on each subsequent token prediction. This is kind of a mental model they paint for one interpretation of what's going on as these LLMs do this kind of reasoning. And they mention that some of the tokens are incredibly specific. I mean, the word "the" is the most commonly used word in English language. And I think they detected hundreds and hundreds, or several hundred features for the word "the" in very specific context. So there is a feature for the word "the" in a physics context, and there is a feature for the word "the" in a chemistry context, and a feature for the word "the" in, I don't know, like a traveling context or something. So like it's quite unintuitive to what features are expected, and it seems as though they make an argument that it's more efficient to have a somewhat compositional feature set, because if you had all of the features totally disentangled, it kind of requires more work for the model to kind of detect the word "the" being turned on, detect the word physics being turned on. And if you have this very large sparse feature set, there is some means by which it makes sense to kind of, and it's very common that you want to talk about something related to physics. It makes sense from a computational efficiency standpoint to have that kind of baked in as a dual concept, basically, is the point they make. Loosely, I mean, I might have busted the explanation a little bit, but this is an interesting point they made. Okay, then they talk about related work and discussion, and then they talk about all kinds of interesting things, which is like, so yeah, they talk about this point here, which is they originally thought that superposition would give them this isotropic superposition where all of these features are kind of uniformly distributed in space. What they actually find is that there are these clumps where they have lots of different features that group together on like really important topics, which I guess makes sense because you basically have some concepts that are more important than others. And of course, increasing the likelihood of talking about astrophysics just by virtue of how networks work in this kind of continuous space needs to kind of increase the likelihood of talking about particle physics or something, because you have this kind of continuous medium of these latent representations, and it makes sense that similar concepts need to cluster together, and concepts that are very important but do need differentiated boundaries need to be clustered together. So they basically see that there is this very clear clustering, and you don't have anything like an isotropic distribution. It's much more like this. Currently, their hypothesis is that the features are one-dimensional in so much as you represent the feature obviously using lots of different vectors, but actually the feature is on or off. It has an activation level. You can, the magnitude of this direction is effectively what the feature is representing. Another hypothesis is that actually it could be a feature manifold where one monosemantic feature is expressed as the value of this feature is expressed as a two-dimensional vector and not a one-dimensional vector. Although they do make this point that it's very similar to having a lot of monosemantic one-dimensional features and then looking at the convex hull of those features. So if you imagine like 5 different features in this like high dimensional space, and then you compute the convex hull, the surface of that convex hull does represent a kind of a surface representation of a feature. The question is that enough, or are these features actually inherently multidimensional and inherently represent a manifold that cannot be expressed by a convex hull of these kind of one-dimensional features? That's an open question still. Yeah, lots of interesting things, and lots that I'm very excited to look at as to what they've learned in the Haiku model, because all of this very deep complexity was applied to a one-layer transformer with 512 activations, like a tiny transformer that's comically small, and we have tens of thousands of very clear features emerging. So it does like set things up to see what are these massive networks learning. How many features are there really there? Like, are there trillions of features potentially, and how specific are they? And yeah, so I'm excited to go through the second one at some point in a reading group. But I think that'll do for now. We're already 5 minutes over. I realized that was quite dense. I would suggest maybe if anything you didn't follow, maybe watch the video again, or better yet, read this in lots of detail. I think this is really important. I think this paper and the paper following it are going to be like foundational works. It's the first work that's really gone into detail, trying to understand what's going on in transformers, and they make a very compelling case for what is going on. I think this not only transcends to AI, I think this is very relevant for neuroscience, assuming that cognition in the brain, also of which neuroscientists have found that neurons are not monosemantic. When you find one neuron, it's very hard to tie what it's doing. It could be the case that the brain is also, the neuron activations in the brain are also projections of a high dimensional, like much more monosemantic space with this dictionary learning. Of course, it's very hard to test that because you can't rerun experiments of the brain or artificially turn activations on or off. I mean, maybe you can with Neuralink a little bit, but it's obviously a lot easier to do experiments with transformers than it is to do experiments with the brain. So I think, I don't know, I think this is a very fundamental piece of paper when it comes to how intelligence and how cognition works, fundamentally. So definitely something I'd recommend everybody reads and tries to make sense of. But anyway, that was, so I find this paper really exciting, but very happy to answer any questions anybody has. And again, I apologize if it was a slightly dense one. It's quite complex stuff there. Okay, so I see some questions. So Cato Stevens says, how can these interpretability techniques be integrated into existing AI deployment pipelines to monitor and just model behaviors dynamically? Well, I guess for open source models, you can just copy what they did, and then you can have dials for the semantic features you get, and you can tweak them, turn them up, down, and like artificially suppress them, like as the model is being queried. So I think it would be quite easy to do this for Llama 3 and stuff. I guess the guys at Meta are probably experimenting with this. For proprietary models, there's nothing we can do because you very much need access to the model weights to do any of this. But I assume that this is the kind of way that models will be aligned and will be steered going forwards, because RLHF is, it's like a very brute force tool compared to having every concept that the network knows about and tuning them up, tuning them down until you get the best performance. So I think this is how alignment will be solved going forwards. But as a researcher, you can only do this with open source models. Ogban.
Yeah, thanks, Dan. Yeah, I'm kind of like, what is the intuitive definition of a feature? I'm struggling to see the difference between a feature and on neurons, or I think I joined a bit late, so maybe that's
Sure.
why. But I don't really know why it's called a feature as opposed to a neuron, or is it a group of neurons or a manifold of neurons in the neural network or something? It's not very clear to me.
Sure. So the feature is just basically a vector in some space that has a direction and a magnitude that can be combined to create the neurons. So basically, the feature definition is given here. So this is what the feature is. This is the equation. So basically, you have your activation vector. So this is 512 values that give the activation, basically, if that makes sense. And data point J is kind of for some given token or whatever. So this is your activation, your 512 activation vector. The feature is basically some magnitude and direction. There's a direction vector as well, but it's basically some magnitude of how much this feature is or isn't turned on based on this data point. So it's actually the feature is learned from the activation, which is it's an autoregressive thing. But actually the point is that when you add these features together and when you add their corresponding direction vectors together with a bias, you recreate the activations basically. So you can think of it as kind of like a higher dimension, like a set of many more vectors which can be turned on and off, and when turned on and off in certain combinations, recreate the activations in the neuron. But you have many more features than you have neurons. So this is 512, but you might be summing over 4,000 terms here. So it's kind of like a set of concepts which, when added together, create the activations we see in the neurons. That's basically the definition of what the features are. The question is, does such a set of features exist? Like, do they exist? And can we find them? And that's the job of the autoencoder, to try to have this constraint to make sure that the features remain sparse. And if we have this very large number of sparse features, are they more semantically meaningful than the activations we get? And the hypothesis is that there are many more features learned than there are neurons. So you can have hundreds times more features, concepts that the network's able to learn, but because of the capacity constraints, you can't represent all of them as independent neurons. So the neurons represent these features via this kind of superposition, basically expressed by this equation. This is basically, so it's the same thing. It's just that the network doesn't learn the features as independent neurons. The network kind of, learns to represent the superposition of a much larger number of features, basically. So it's kind of an abstract concept. But the hypothesis being that the network is effectively reasoning in this kind of high dimensional semantic space, basically. Hopefully that made sense. But this equation is the crux of it.
Yeah, thanks.
Sure. Any other questions at all? Okay, well, I'll assume that I may have lost some people, not only because it's a complicated topic, also because, I don't know, my explanation abilities aren't always, I hope they're somewhat helpful, but I would definitely recommend reading through it. But I think, like, if there's anything you're going to take away, it's that it seems as though networks reason in a much higher dimensional feature space. Networks that have a very small number of activations, even 512, they are able to represent and understand many thousands of concepts which are very specific to particular contexts. They're able to understand the concept of Arabic language, Hebrew language, physics topics or whatever. And there's a very mathematically detectable way to see that the network has like understood this concept. You can see that these features do and don't trigger in the very specific relevant context. It seems as though networks are leveraging superposition to kind of represent these many concepts in a very small number of values. And this gives us a very meaningful way to steer LLMs to control what they can do, to turn up and down different concepts in this kind of very simple combinatorial way. And this is all profoundly interesting. I didn't expect that something so simple as a 2-layer autoregressive sparse autoencoder with like an L1 loss on the intermediate representation, I didn't think that out would just pop totally semantically understandable features, but they do. So that's super interesting. And it suggests that maybe the alignment problem in AI is easier than we thought. I mean, let's not jump ahead of ourselves, but if we do have these knobs, if we can build an LLM and have a knob that's like toxicity or a knob that's like rudeness and just like turn it up or down, then it just suggests that, it also suggests that mind control, if like that's how the brain works, it just suggests that if all it takes is somebody to turn one feature that represents like aggression or something and like we suddenly get angry, like, it suggests that maybe like intelligence itself is incredibly hackable, which I guess is, I don't know, good for alignment for AI, maybe bad for the future of Neuralink, I don't know. But it's very interesting nonetheless. Okay. So anyway, well, thank you very much for joining, everybody. Again, I'd recommend going through the material to make sense of it, but this is a really foundational paper, so I'd really suggest everybody reads it and tries to understand it. Yeah, thank you so much for joining, everybody, and see you guys all again same time next week. Thanks a lot. Bye-bye, everybody.